Okay, welcome to exponential graphs. This is Unit 6. Mostly I just call it exponential graphing. For Algebra 2, the essential questions: what are the characteristics of exponential functions? Okay, we have looked at this in essence of sequences in class, and basically you really want to look at your growth rate right here. So looking at that, we can just go ahead and write our sequence. 2 to the negative third is 1 over 2 to the third, which is 1 over 8. And 2 to the negative second would equal 1 over 2 squared, which equals 1 to the fourth, 1/4. Would you go ahead and continue to fill these out? The only one that might stump you is realize the pattern. 8 divided by 2 is 4. So you can look at the pattern here. It will be 4 divided by 2 is 2. 2 divided by 2 is 1. So this will be 1 over 1, or 1. And then 2 to the first, 1, actually, I shouldn't be saying divided here. It's actually times 2. Wow. 1/8 times 2 would be a better way to look at it. It does end up resulting in what looks like it's divided. I'm just looking at the visual pattern there. But it's important that we say that it's times 2, because what's going to happen here is it reduces that bottom number. But now on this one, 1 over 1 is 1 times 2 equals 2. Okay, and then you'll just be building up. All of these are building up. They're getting twice as big as what the previous number was. So when you come over and graph this, at negative 3, 1/8 is just barely off of the x-axis. 1/4 is 1/4 the way to that first line. 1/2, halfway to the first line. And then 2 to the 0th power is at 1. This is what I call the vertex of a exponential function, is right here at the 0. That's what I always look at for my vertex. As you go to the right, each gets twice as far from that x-axis. So this was at 1, that'll be at 2. Twice as far from 2 would be 4. Twice as far from 4 would be 8. So you can see the growth happening here. That's what we refer to as exponential growth. It just seems to gain speed as it goes. Kind of like a snowball going down the hill. Okay, what happens to f of x as x increases without bound? So as the x goes this way, what's happening to the graph? It's increasing without bound into infinity, isn't it? So that would be the answers on 1a. Does the graph intersect the x-axis? Is there any way to get it down to 0? If we go further on our sequence here, 1/8, 1/4, 1/2 is going this way, but what about if we go this way? Can we hit 0? 1/16, 1/32, 1/64. Do you see the pattern here? It's going to get ever so close to 0, but it will never cross 0. It will never hit 0. So that's a great question on exponential, that there is an asymptote right here, and we've dealt with asymptotes a few different times in graphs. So I would like you to go ahead and dash line that as an asymptote. What is the domain and the range of this function? Just a little bit tricky. On the domain, like with so many of ours, there's no limits on the domain. The input can be all real numbers. Okay? Sorry, I'm off the camera, didn't realize it. All real numbers. And the range, realize it won't ever touch that 0, so we have to say, rather than y is greater than or equal to 0, it's just y is greater than 0. If you're using interval notation, you want to make sure not use the bracket this time. It would be like that. Okay? Okay, so now they're going to have you do a couple graphs. I'm just going to step you through how to get this onto the graph a little bit. Remember with our negative exponent that we flip it to create a positive. So 1/2 to the negative third becomes 2 to the third, which is 8. 1/2 to the negative second will become 2 squared, which is 4. And you can always go with this, or you can also start to follow this. Okay? Go ahead and calculate those inputs. You should end up with a nice gentle curve. This time, the curve's going to go this way. And now it asks, what happens when the f of x to the f of x as x increases without bound? As x goes this way and your curve's coming down, you're going to end up with that curve coming ever so close to 0. It approaches 0 as the x goes without bound to infinity. And the next one, how do the domain and range of f of x to the 1/2 x to the x compare with the domain and range of f of x equals 2 to the x? Well, this one has a curve going down towards the infinity and going up as you go to the negative infinity. This one goes exactly opposite from that. They're flipped over the y-axis from each other. And so their domain and range are the same. Domain and range are the same. What do you notice about the y-intercepts of the graphs of 1/2 x and f of x, the 2 of the x? Why does this make sense? Well, let's go back and look at the y-intercept here. It was when 2 was to the 0th power. Anything to the 0th power equals 1. So when x is 0, it's going through at 1. So does that make sense why 1/2 to the 0th power equals 1? Because all numbers to the 0th power equal 1. Go to my exponents unit in the films if you need to understand why. But when x is 0, y will be going through at 1. Because of that fact. Okay, so that explains why their y-intercepts are the same. What do you notice about the, I already read that one, sorry about that. 2D, what transformation can you use to obtain the graph of f of x equals 1/2 to the x from the graph of 2 of x? And hopefully you've already noticed it's just a reflection over the y-axis. Completely reflection over the y-axis is what you would have. It's a transformation to match those. Okay, on topic number 3, the function of the form b to the x is an exponential growth function if b is greater than 1. This is what we first graphed. And we saw it going this way. Do you see how it goes to the right? It gets bigger and bigger. As it goes towards infinity on the x, it goes towards infinity on the y. The decay, as we go towards infinity on the left, on the x, the graph begins to go less and less and less down to towards 0. It never hits 0. So you would write that in the end behavior as x approaches infinity, the f of x approaches infinity. As the x approaches negative infinity, the f of x approaches 0, because this is for your growth function. That's this one. On 3b, describe the end behavior on the exponential decay, so you need to make sure and write that one. Okay. And what I'm meaning by as x approaches infinity, I just write it like that. Then the f of x approaches, and what does it approach as we go out this way? You should put a 0 there. Okay, Explain why the point 1, comma b is always on the graph. Well, let's look at what 1, comma b is. If we have b to the x, b, and we put 1 in, any number raised to the first power would equal that number, wouldn't it? So that would be explanation. I would like to see it in your own words. Explain why the point 0, 1 is always on the graph of b to the x. Well, now we're plugging in 0 for the x. And any number to the 0th power equals, that should be your answer there. Okay, are 3 to the x and 5 to the x both exponential growth functions or both exponential decay functions? Although they have the same end behavior, how do you think their graphs differ? Explain your reasoning. Remember back to the front page and what we saw the numbers increasing by, what factor they were increasing by. That has to do with your base number. And then think about how that would affect the curve of your graph. And I would like to see your reasoning there. We'll talk about it in class. Okay, on 3f, f of x equals 1/3 to the x and 1/5 to the x. Are these exponential growth functions or are both of them decay functions? And if you're having trouble knowing, look back up here. For decay, it says if the b value is between 0 and 1, then it's a decay. If it's greater than 1, then it's growth. Okay, and now you'll explain, although they have the same end behavior, which is like the decay, same end behavior, how do you think their graphs will differ? Explain your reasoning. And again, it's by how much they're decreasing. As they come down, you're dividing by 3 on one, you're dividing by 5 on the other. So how quickly is it falling? Put that in your own words, your reply to that. Okay. On the next page, it says, compare each of the functions. F of x equals x plus 3, g of x equals x cubed, and h of x is 3 to the x, where x is greater than 0. So we just want to see what happens. When we plug in 0, we get 3, we get 0, and we get 1. I'd like you to stop and make a prediction here. What's going to happen? When we plug in 1, 4, 1 cubed is 1 times 1 times 1. 3 to the first is 3. 2 plus 3 is 5. 2 times 2 times 2 is 8. 3 times 3 is 9. So I want to make sure that you're doing these right. You go 3 squared. Here you're going 2 cubed. And here you're just doing 2 plus 3. Now I'm sure you can find right now which one will be the slowest in growth. But I'd like you to predict which will grow quicker. Overall, to the end, will it be this one or this one? And then please go ahead and do the math to prove which one you think. Just put your prediction out beside here right now. We're going to talk about salaries and allowances, and it's important that you choose wisely when we come to that. Okay. The graph h of x equals 3 to the x is shown on the coordinate grid below. Graph x plus 3 on the same coordinate grid. X plus 3 is a linear function. It's this function, that was that function. Okay, going back to graphing linear, remember we go to the y-intercept, so it's at 3, and then we rise 1, run 1 with the slope, and please use a straight edge of some form. So we have that. The graph of 3 to the x is shown in the coordinate grid below. Graph x cubed on the same grid. Okay. 0 cubed is 0. 1 cubed is 1. This is your cubic function that we've done in the past. 2 cubed is 8. Whoops, I'm not using their grid correctly. 0, 0. 1 cubed is 1, so it'd be way down here. 2 cubed is 8. Well, if that's 40 and that's 20, 10 would be halfway. It's below halfway. 3 cubed is 27, be about there. 4 cubed is 64. 5 cubed is 125. So you can see what happens graphically. Okay? How do the values h of x compare to those of f of x and g of x as x increases without bound? Okay, always be able to explain your reasoning by what you have up above in your proof. I want you to prove these things and then explain why it happens. Remember in class, the why is much more important to me than the right answer. Okay, good luck with that. I believe that's the end of that lesson. Yes, tomorrow in class, we'll be working on these practice problems. So if you miss class, then you'll need to come in and make up some time in tutoring. 6-1.